Understanding of how predictable weather is, in that if you're told that it's going to rain tomorrow, you'll think that's likely. But if you're told that it's going to rain in 3 months' time, you'll think that that's a bit less likely. So we understand that there's some range of predictability, that at early times we have more predictability than at late times. And we also have this idea of the butterfly effect, whereby a small change at small scale can influence a large change at later times. So that implies that your small change, your perturbation in the system, must grow exponentially. So we have an exponential growth of error, but we also have this sort of long-range predictability. So turbulence in the atmosphere is dominated by, weather in the atmosphere is dominated by turbulence. And so specifically, this shouldn't be a blank slide.
Okay, but so have you had any like movies there?
No, it should, like if you go out of it, then
Okay.
that's
Okay, that's right, but
so if you scroll.
yeah, it's a bit punched. Okay, just keep it maybe this, and I hope it's not going to happen anymore.
Okay. So I look at homogeneous isotropic turbulence, and so if we have a second order correlation function R, it's these angle brackets represent the average over all space, and so homogeneous means that your second order correlation function is only a function of the relative distance between the 2 points. Isotropic means that you have the rotational variance of the axis of your bases, and then stationarity means that the statistics of the flow are somehow independent of time. So this is an example of homogeneous isotropic turbulence, and physically, what's happening here is that we have a grid, and then we have smoke which is pushed through this grid, and we have a turbulent pattern generated behind it. Now, if you have a small enough box, then you can see that the statistics of the flow will not depend on, beyond a certain point, will not depend on the translation of rotation invariant. Okay, so we don't actually look at experiments, we look at simulations of homogeneous isotropic turbulence. So this is the
This was the next one?
This is the next one.
That's, okay. Just let me. It's PDF, so you should be know like type of problem, apparently.
Do you have another reader?
Another like
PDF.
Yeah, do you have another PDF? Oh, another reader of the PDFs.
Microsoft Edge.
Yeah, let's try it then. It's actually a brand new laptop, so I haven't tested it on the cloud. And now how we make a full screen here?
Usually it's this one. You should have one.
Right hand corner.
Right corner, right corner, this one.
Oh, yes.
Okay, we're gonna. I don't know.
Okay, no, that's not good. Again. Okay. No, okay, I understand why it happens this way. This is just the screen.
Probably maybe try to use the Zoom.
Zoom. Let's know this. Okay. No, let me just. Okay, and now if you.
It's going to start.
Yeah, it's going to be.
Let's try.
Alright, so sorry for this inconvenience. Let's continue this way. I hope that's not going to be, you can
Okay, so
either scroll.
Okay. I'll scroll up when it becomes needed. Okay, so we have this, we solved an average Stokes equation in a periodic domain of length 2 pi. We have incompressible turbulence, so we have the default U is 0. Okay, turbulence is quantified by the Reynolds number. This is the ratio of the inertial to viscous forces. So if the viscous forces are very high, you have your fluid is essentially damped and the motion becomes laminar. And if your inertial forces are very, very large, you have turbulence. So to have turbulence, you generally need the Reynolds number to be much, much bigger than 1. Okay, so this is a non-dimensional number with UL over viscosity. U is the typical velocity of the system you are looking at, and L is its typical length. You can further quantify the turbulent energy in the system with the energy spectrum. Unhomogeneity we can define it like this. With U hat is the Fourier transform of the velocity. The turbulent energy spectrum defines at what energy the turbulence is mainly located, where k is it's an inverse length. So when I say low k, I mean the largest scales. When I say high k, I mean the smallest scales. So if ek is high at low k, that means the energy is dominated by the large scales, and if ek is large at high k, then it's being at the smallest scales. Okay, all right, that was length box. Okay, phenomenologically we have the Kolmogorov-Richardson cascade. So phenomenologically we can think of turbulence as we generate it by a instability in a beam flow. So we have two flows going past each other, and instability with different speeds, and an instability generates the generation between them. Now you have this large scale structure at this instability, which is called an eddy. These eddies are basically lines of vorticity. Now these large eddies then break up into smaller eddies, right? And so these smaller eddies then in turn break up into smaller eddies and so on, until you get to the very smallest scales where, because we have a Reynolds number, we can find the U and an L for these smallest eddies, and at this point the Reynolds number will be roughly 1. And so these smallest eddies will then dissipate. So we can characterize this by a cascade of energy. So when there's a breakup of a larger eddy and a smaller eddy, the larger scale gives its energy to a smaller scale, and so on and so forth. And in the cascade picture, the flux of this energy is constant, and we have a long chain of local inertial transfers. The flux along all scales is equal to the dissipation rate by energy conservation, and that we have to have, if you have energy going out, which is dissipation, you have to have energy input as dissipation. Okay. And using the Kolmogorov-Richardson cascade phenomenology, we have the energy spectrum goes like minus 5/3, which is the 5/3 law. Okay, so we can define these Kolmogorov scales, which are the smallest scales in the system, whereby the Kolmogorov Reynolds number is 1, and we have this Kolmogorov time scale, which is going to be used by the square root of the viscosity over the dissipation. Okay, so I look at simulations of turbulence, and the Reynolds numbers we use in our simulations are at most about 2,000 or 3,000. So this is a typical energy spectrum I have for one of our DNSs. Now, the Reynolds number of blood flow is smaller than our DNS, but the Reynolds numbers of most more common seeing turbulence like a person swimming or behind an airplane is much, much higher. So you might wonder how relevant our results are, given that the Reynolds numbers are so much smaller than actual physical values. But we don't have infinite computing power, so we have to accept these. We were originally actually motivated not by weather, but by astrophysical processes. And so these will have Reynolds numbers even further beyond the solar convection zone. We were thinking of large galactic scale fields. So if you think it doesn't apply to weather, it really doesn't apply to what we were looking at originally. Okay, so if we're going to look at turbulence in an Eulerian sense, we'll have to have a mental picture of what's happening to the turbulence. So we can have a chaotic saddle picture. What happens is that the state space of the Navier-Stokes equation is dominated by these turbulent chaotic saddles. These are, yes, but there's also these laminar stable regions. And so what happens is the turbulence pings between these chaotic saddles, and then it can spontaneously relaminarize if it reaches one of these laminar regions. And so if we have this toy model of turbulence here, in an Eulerian sense, what we have is a chaotic...
when you say relaminarize, you mean that the turbulence is vanishing?
The turbulence just vanishes completely.
Okay.
So when it reaches one of these laminar regions, it just disappears, basically. And we have a laminar...
Is it like, does it depend on the, somehow, I don't know, how much energy the turbulence is carrying? If it is a relaminarization?
The relaminarization happens with a super exponential lifetime dependent on the Reynolds number.
Okay,
so it's like a nuclear decay,
okay,
but not the Poisson process. Well, it is Poisson. It has no memory, but it's a super exponentially dependent on the Reynolds number. Okay, so we have a toy model of what our state space, which is a period, a repeated chaotic saddles. And what happens is, if we start our system, the red squares and the black circles are two different initial realizations. What happens is, we initialize two of these things in this toy model, and they diverge. They start diverging exponentially whilst visiting these chaotic attractor, and then when they're far enough apart, they are no longer within the region of the same chaotic attractor, and they start just wandering, exploring the state space randomly. Sorry.
Could you explain what is a chaotic saddle?
A chaotic saddle is a, well, if you imagine a linear, do you know much about linear stability? Okay, so you have a saddle node. Well, it's like that, but chaotic. So you're...
and maybe you can draw it like, I don't know, just you know, the linear stability.
So you have this
diagram.
So you have a so you have a point here and a point here. They will, even though they're close together, they will eventually diverge exponentially. So this is the state space. This is a saddle representing the state space of the system. So you can imagine a set of these saddles just repeated through state space. Okay.
Thank you.
Now, compared to that picture, we actually have a the turbulence is actually has a we have constant energy, right? So instead of it being a flat space, we're actually can imagine the random walk as happening on. It's a random walk. Well, we can imagine turbulence as a random walk between these chaotic saddles, and it will be a random walk on an n-dimensional hypersphere because we have constant energy. Now, someone else has worked out that if theta is the angle between the point and its origin, if it's undergoing a random walk on an n-dimensional sphere, we'll have cos theta goes as an exponential of time. Now, if we have the difference where the difference is the Euclidean distance between the point and its origin. It should grow as 2 times E, where E is the turbulent energy, 1 minus this. Okay. So we put this in our experiments. What we find is that we measure, we evolve the system, and then we capture the point at a single point in time, and then let the system evolve, and we compare it to its original space, and the distance between it is the Euclidean distance. And red is the measured result, and the dashed line is a fit to this mental picture of the random walk in one-dimensional hypersphere, sorry. And we see that the fit is roughly good, is quite good. So this mental picture is okay. So we use DNS simulations of turbulence, and what we do is we have a pseudo-spectral code, which means that it does some of the calculations in real space and some of the calculations in Fourier space. And it's fully de-aliased, and it's on a periodic cube of length 2 pi, and our fluid has unit density. Okay, we vary the viscosity to vary the Reynolds number, so we keep the dissipation fixed, which we can do because we have this negative damping forcing, which allows us to know the dissipation beforehand. We solve the Navier-Stokes equations, and we have box sizes not to 204A cubed, which is quite big. Okay. So what we do is we evolve the system with the Navier-Stokes equations, and we're wanting to measure the chaotic properties. So what we can do is, once it's reached a statistically steady state, we create 2 copies of the evolved field, we perturb one of them, and then we evolve them both independently. And then we can track the error, or basically the difference between them. This is called the error. And the error allows us to find the difference spectrum, which will quantify at what scale the difference between the 2 fields is located. So if our difference spectrum is dominated at low k, then the difference between the 2 fields is only in the very largest structures, and the small structures are identical. And alternatively, if the error spectrum is very large at high k, then only the smallest scales are different, and the large scale structures are essentially the same. So what we find is that the error spectrum must adopt a certain characteristic spectrum, which I'll describe in the future, before the total error, which is the sum of all the errors, grows exponentially. Okay, so what's happening qualitatively? So we find these 3 different states. First, we have our low Reynolds number state, which is, Reynolds number is roughly 1.2. So what happens is the error just drops a bit, and then we stay, these 2 simulations stay within a certain tolerance of each other. We also have these relaminar states, so when I talk to you about the mental picture, we have these relaminizations that occur, and these are actually linearly stable. So these relaminar states are actually qualitatively different from the just the low Reynolds number situation. And we also have high enough Reynolds number with this exponential divergence of the 2 fields, so that this is the hallmark of chaos, basically. The 2 systems diverge exponentially. Okay, so what happens if we look at the error spectrum? If we create a difference at the largest scales, what we find is that what's happening is that this is early time, and then progressively we go up and up in our graphs. So time is rising up with the plot. So what happens is that the smallest scales have to become sufficiently different before the largest scales will even start to diverge. Okay. So this is the system adopting this characteristic spectrum, which is shown physically here. This is the characteristic spectrum it has to adopt. So we have this at low k we have a parallel. So the largest scales, are very similar compared to, say, the intermediate scales. And this is a Walpole plot, so this is a parabol. And we find that the large wave numbers actually have an exponential dependence on the wave number. This is the wave number, so this is the scale. So this is the largest scale, and this is the small scale. Okay. The peak of this characteristic spectrum is 1 over this slope here. And we can measure this slope as it depends on the Reynolds number.
And this is like after, so previously you show how this evolves with time?
Yes.
So this is like the long-term behavior?
This is the long-term behavior whilst it's
Okay.
still growing exponentially. Whilst it's still growing exponentially, it will adopt this spectrum, regardless of Reynolds number with character, well, with this
So,
power
but
law.
do you have some intuition, like, you know, like the peak here, is it like, you know, this small turbulences get somehow accumulated to raise the difference on the larger scales, or is it like independent, the large scale behavior from the?
Well, no. This shows that the smaller scales have to become sufficiently different before the larger scales
Okay.
can then actually become different.
But so in principle, it's always like this, that you know you need to have differences at the
Yes.
shorter scales to have
Before,
them on the
yes.
larger.
Yes. So we can measure how this slope here depends on the Reynolds number. And we find that it drops with Reynolds number so that this slope here will become essentially flat at infinite Reynolds number. So we'll only have this large power law behavior, a large Reynolds number. Okay, if we take this all together, we have a recreation of the butterfly effect. That, as I was saying, the smaller scales have to become, we create a difference in the smaller scales. We create, these grow exponentially with time, and eventually they start to affect the larger scales and bring them up. Okay, so when people first looked at the butterfly effect, they did it in atmospheric models of turbulence. These atmospheric models are supposed to capture the turbulence, but they do not directly model the, they do not directly evolve the Navier-Stokes equations. So what we see here is that the butterfly effect is actually a fundamental part of the turbulent evolution, and the butterfly effect is not an emergent part of the model. It is somehow capturing the real behavior of the turbulence. Or
What do you mean by saying, you know, it's not emergent feature of the model?
well, I guess it could be an emergent feature of the model, but it is capturing something that is happening in the turbulence. It's not something that's just happening because they modeled the turbulence in a certain way. What else was it? We've not looked at Amsterdam. This is our interpretation of our data. Okay. We've got the Kolmogorov scale and dash 3. Okay, so the main point of the work was to actually measure the level of chaos in the system, which you can quantify with the maximal Lyapunov exponent. These infinitesimal perturbations in chaos will grow exponentially, and they will do so with a certain rate, which is given by lambda. Now, in a Lagrangian sense, what we do is we have a flow, and we embed these tracer particles in it. And these tracer particles will grow exponentially far apart with a certain rate. What we are looking at is the Eulerian sense, so we have the state of the whole system, and the state of the whole system diverged exponentially from what it would have been. So, intuitively, you would expect that the more turbulence there is in the system, there should be more chaos. And the only theoretical prediction of what the lambda should be is 1 over tau, where tau is the whole number of time, which is the eddies, the turnover rate of the smallest eddies. The reasoning behind this is that tau is the smallest time scale. And so if you want the largest lambda, you have the smallest time scale. That's basically tau. And we varied the Reynolds number, so we varied our parameters. We found the difference between the Lyapunov exponent and 1 over tau, and we find that it's roughly linear, which is nice. But there's a problem in that tau only indirectly measures the level of turbulence in the system. There's no Reynolds number in this, so we want to include a Reynolds number. So we can create an alternative prediction of what lambda should be, which is which relates 1 over tau to 1 over t naught, where t naught is the turnover term of the largest eddies, and we'll have a Reynolds number dependence here. So you have this alternative prediction here. Now, from Kolmogorov, the Kolmogorov cascade theory predicts that alpha is 1 over 2. So you can test this, and we find is that we have this rough power law behavior between lambda t naught and RE, and the dashed line is a half, and our straight line least squares fit is almost a half. You might wonder that we've got this sort of large error here at low Reynolds number, but because it's a log plot, this looks worse than it actually is. But then you've got another problem with this, in that for every flow, even if it's not chaotic, even if it's not turbulent, we can define a Reynolds number, and we can define this t naught and lambda. So we somehow want to integrate the phenomenology of turbulence into the system. So we can create a second prediction, which is that since our Kolmogorov scales are RE1, somehow our theory says that they're driving the turbulence, but we don't even know that they're properly chaotic. So we choose the largest velocity, which is the RMS velocity, and the smallest physically relevant scale, which is the Taylor microscale, which is the, these are basically the eddies which are responsible for most of the dissipation. So we just suggest that lambda goes like the ratio of u over the Taylor Reynolds number, the Taylor length scale, sorry, and we get this Taylor Reynolds number dependence, where the Taylor Reynolds number dependence. And we can measure that with our data, and we get this nice straight line fit. And what's very nice is that this goes through 0, even within 1 standard deviation of a fit. So there's somehow only one parameter in this. But then we have another quibble with this, which is that our lambda is somehow capturing some sort of information generation in the system. So we can just a priori suggest what the relationship should be using only our information theory thing. So we've got, in terms of information, we've got the energy, which is somewhat proportional to the amount of information in the system. And if you have more energy in the system, you can encode more information in it. We have a dissipation, which is proportional to the level of information. Well, actually, it's proportional to the level of information loss in the system. But because we have a statistically, we have a roughly steady energy, this should be equal to the amount of information put into the system. And then we also want to include the Reynolds number, which is proportional to the amount of turbulence in the system. So we include our physicalized sense that our Reynolds number, our things should become more turbulent with a higher Reynolds number. So this fourth prediction, and then we can use our data with that, and we get this other straight line fit, well, this other log fit, sorry. So what we can do is we can compare all these fits together, and well, we don't really know which one of these is right. Well, we can't know which one of these is right unless we took more and more data. So what we did was we looked at decaying turbulence. Now, our Navier-Stokes equation has this forcing term, which we set to this large scale forcing before. So what we can do is just set the forcing to 0, and what will happen is our energy will decay as a parallel in time. Okay. And we then generate a theoretical prediction of what the exponential growth of error should look like if we have a energy which decays as a parallel in time. So we have two parts of this equation. Essentially, we've got this exponential growth part. The system should grow exponentially far apart because it's chaotic, but also the whole state space of the system should shrink because the energy is decaying. So this is for one infinitesimal type step, and if you do, if you expand this so that it goes from time 0, which is time I, the initial time, to n, the final time, we will predict that an error should grow like this. So what we can do is we have these 4 different predictions, and then we instead of having lambda, we have lambda as a function of the time, and so we know how the commodal of time depends with time, how the large eddy turnover time depends with time, and the Reynolds number depends with time, and so on. And we use the decaying system, we perturb it slightly, and then we predict what the difference would have been given these functional dependence for the outcome exponent. And then we can compare it to what we actually measured. So, and the fits we use for these are from the force data. So what we get is this. These are our 4 predictions. So in the force data, they looked relatively equivalent. But what we find is that this one, this red one, which is the information theoretic one, actually produces results which are quite close to the, or very close to the measured result, whilst the other ones are orders of magnitude wrong. So using this other test, we can say that this one's probably more right than the others. Okay. What we can also look at is we have the late time behavior. So from way back at the start, we know that the predictability of time of the weather is finite. So you know that tomorrow, if they say it's raining, it will, roughly. But how do we reconcile that with our log dependence on the Reynolds number? So the atmosphere has a very, very high Reynolds number, which would imply that the Lyapunov exponent should be very, very high. And if we create a small perturbation in the system, it should completely dominate our prediction. So the atmosphere shouldn't be predictable at all. So we have this, we started this thought experiment that how would you go about measuring the Eulerian level of chaos within one experiment? I mean, you can't create 2 identical systems. So what we theorized was that if you have 2 points, F and G, which are far enough apart so that they're completely decorrelated, and then, but the statistical behavior of the field around them is identical, like exactly the same. If F and G are initially very similar, then that should be like measuring the difference between 2 identical points, which we perturb slightly. So we can exploit, and so we start with initial delta, which is the difference between F and G. So you can see that the time dependence of delta squared, which is proportional to our error, was this. Now, we exploit isotropy. Isotropy implies that we don't actually need to have 2 which are sufficiently far apart. We just need 2 components of the same point in space, which are orthogonal. They will be completely independent, but they will have the same statistical field around them. And we can generate the prediction that the average change of the error should be this, but from our energy equation, we can note that this, which is equal to the dissipation rate. So we have a prediction that at late times, the error should grow linearly with the rate given by the dissipation rate. And we looked at the late linear time. So this is the error with time, and these are 2 different simulations. And this dashed line is proportional to the dissipation rate times time. So you see that this late error growth is captured in our data. So this could just be a coincidence that we picked the right dissipation number. So we then vary dissipation independently and measure the late slope, and we find that there is sort of linear dependence between the late slope and the dissipation, which is nice. So not only is the ability of the predictability of weather possible because of the model, it's actually also reflecting a fundamental part of the turbulence itself as well, as a butterfly effect. So. Okay, so we can measure the predictability in a different way, which is with the covariance. So the covariance is sort of the relationship between two variables. So if the covariance is 1, they are completely correlated, and if it's 0, they're uncorrelated, and if it's -1, they're anticorrelated. So we can define the self-correlation with time as the correlation of a variable with itself after a given time delta t. So if delta t is 0, it's 1 because they're completely correlated. And we expect that if delta t is large enough, then they should be completely decorrelated in time. Now, at what sort of time will they become completely correlated? Well, since we have the error growth goes like epsilon times the dissipation times time, the maximum value of the error is 2 times the error because of the way we have 2 times the turbulent energy because of the way we defined it. So the minimum time at which it takes for a large scale of 2 fields to become completely correlated should be 2 times T E naught, where T E naught is U over dissipation. Okay, so we measure this for a large system, and what we find is that if you put 1 minus the self-correlation in time at 1, they should become decorrelated. What we find is that when we measure this self-correlation with time, they became decorrelated about t equals 11, and if we look at our actual data, we find that 2 times the large eddy turnover time, or the 2 times E over the dissipation, is 10.86. So this is very close to what we actually measured as our correlation time using this other method. So there's obviously a link between the two. What we have further done in other experiments is coupled the fluid to a magnet. We've made the fluid magnetically conductive, and so when it moves, it induces a magnetic field, which then affects the behavior of the velocity itself. And the evolution of this is described by the magneto-hydrodynamic equations. And what we found is that the Lyapunov exponent depends not only on the Reynolds number, but by this magnetic Prandtl number, which is the ratio of the viscosity to eta, which is the diffusivity of the magnetic fluid. Sorry. And so this linear behavior that we found for hydrodynamics is separate for the 2 fields, and it depends independently on the dissipation rate given by the U field and the dissipation rate given by the magnetic field independently. So they don't have the same linear rate of separation. We also find that the magnetic helicity, which is somehow the knottiness of the magnetic field lines, limits the error growth. So that if magnetic helicity rises to the maximum value, then the maximum it can possibly be, which is given by some realizability condition, you will have actually no error. So in some way, the helicity is making the system more ordered. Okay, so
that does mean that it kind of laminarizes the system?
it doesn't laminarize the system. It still looks, the thing is, with the helicity, it still looks like a turbulent system, but it's no longer chaotic in an Eulerian sense. So although it evolves very strangely, it's somehow ordered. Strange. So from this talk, we've seen that we can picture the turbulence as a chaotic saddle, as a point in state space movement amongst these chaotic saddles, or as a random walking in sphere. We have this error spection which must adopt a certain type, certain profile before we have this exponential growth. We have the butterfly effect is a fundamental part of turbulence. We have shown what the dependence of the Lyapunov exponent is, and we have this late linear time, late linear behavior, which is also a fundamental part of turbulence. But it's also captured in these atmospheric modes. Thank you.
Do we have any questions?
Yes.
Did you test those predictions also in 2D models? Because then the Kolmogorov prediction is different. It's upside down, right? For the energy flow.
Well, our initial code was 3D, and you know how people normally go from 2D to 3D codes? We had to make our code 3D and then make it to 2D, which is actually a bit more technically difficult. And we are currently measuring that. So one of the PhD students, younger than me, he's below me, he's measuring that. And I think he's finding that it's, instead of being dependent on tau, it's on the entropy turnover. So if you define tau, instead of it being with dissipation, you define it with the entropy dissipation, then you'll have a rough linear behavior between the Laplace and entropy. So there isn't actually a dependence for the Reynolds number between lambda and the Reynolds number in 2D fluid. It's based on entropy.
Any question here?
If I got another question, you showed us a peak or a hinge on one of those LG plots. Is this artifact or is this physical?
Which sir?
I
I think I know what you mean.
much earlier.
It's this.
Maybe this, yes.
Oh yeah, this is just the artifact
Okay.
of the simulation. The more unresolved your simulation is, the bigger these things become. And so some people will just cut off their plot at a certain wave number to hide the fact that their simulations aren't very well resolved.
You also had, you showed those 4 predictions, and then you showed like for the relation between lambda and the Reynolds number that were time dependent, and then you put, and they were pretty good. Like you showed the correlation, like linear fit was nice, and then you put the time dependence, and then you have such a spread. Why is it so?
Well, maybe because I'm just speculating here. That you have this I know chaos is an accumulation of error, but somehow the small difference between your prediction and the actual behavior somehow starts to compound with time, so it becomes exponentially worse.
Okay.
Sure.
Okay, then let's start again.